Hey guys, I'm just going to go through that assignment from yesterday. I got a little hookup so we can see what my calculator is saying. So this is the assignment. So all we have to do is so this is how we can see what I'm typing in my calculator to help you out. Okay. So if we want 0.00125, then we would just type in negative log of 0.00125, and then we would get that as our answer. And in terms of sig digs, you want to base it on the question. So in the question, this is a normal number, so we have 3 sig digs, so we want 3 numbers after the decimal place. So our answer would be 2.903. So that's for the first one. I'll do the next one. So 2.3 times 10 to the negative 9. So we go negative log 2.3. And then if you push second comma on your calculator, does that E? And that means times 10 to the, and it just saves you a little bit of time and it's a little bit better. So for this one, our answer would be 8.64, because we'd have to round that one up because we want the 6.3, and then the one before is 8, so it'd be 2.64. For the next one, we would negative log 4.42 times 10 to the negative 13. And, oops. It's got to re-autofocus there. That's bad. Let's autofocus that. There we go. And for this one, we want 3 sig digs, so we would have 12 and then 3 numbers after the decimal place, so 355 would be the correct answer. And for the next one, we would go 5.6 times 10 to the negative 2, so negative log of 5.6 times 10 to the negative 2, so 5.6. Second comma, so E times 10 to the negative 2. And we will want 2 sig digs, that's 1.25. And then for the last one, we can see that it is 8.10 times 10 to the negative 8. So we would go negative log 8.10 times 10 to the negative 8. And that tells us that we get 7.0, so we want 3 sig digs, so 7.092. That's a 0 there. So that would be our answer. Okay, for the other ones in the assignment, so 2.14, let me just write these down so we're not going back and forth. So 2.14, 7.1, 9.437, and 11.00. So if we want to take a look at those on the calculator, so you go second log, and then it goes 10 to the, and you have to do negative. This button down here, not the minus, 2.14. So this one's going to be, we want 2 sig digs, so 0.0072. Or we could also put down 7.2 times 10 to the negative 123. Both would be correct. And then for 7.1, we would just second log negative 7.1. And we get 7.2 or 1 sig dig. It would just be 1 sig dig, so it would just be 8 times 10 to the negative 8. And then our next one, 10 to the negative 449.1 0.37. And that one's got 3 sig digs, so we would do 3.66 times 10 to the negative 10. You can see how it does the E on the calculator there. And then the last one, second log, negative 11.00. And that would give us 1.0, because we want 2 sig digs, because we have 2 numbers after the decimal place, times 10 to the negative 11. And all these should say moles per liter on them. Okay, so that's how you would do those. And let me just look here. Go back to that assignment. What is more hydronium ions, 3 or 5? So 3 is going to have more, and then it jumps 2 pH places, so it would be 100 times more. And then these labels, this is a compressed gas, so I get propane, flammable, propane, oxidizing. You don't need an example for that. Explosive, propane again. Poisonous, something like arsenic or cyanide, things like that. So that's poisonous and would cause immediate death. Biohazardous would be blood or needles. Corrosive would be acids. And this is just less serious other health effects. Asbestos would be an example of that, something that would cause long-term damage over time. Drinking acid would be bad for you. It probably wouldn't kill you immediately if it wasn't too strong. And this is just to point out that it's got dangerous effects, toxic effects. And this would be environmental effects like mercury. Okay, so that's the assignment from yesterday. So let's go through these sample diploma questions. So if the pH of a river is 7.73, then the corresponding hydronium ion concentration is. So try this on your own, pause the video and see if you can get it. I will go through how to do it. So 7.730. So I'll go back to my calculator and I'll just go negative log, because it's a pH of 7.730. And it gives us that as an answer. Oops, that's because that's a pH and I did the wrong one. Sorry, 10 to the negative pH, 7.730. That. And our answer would be 1.86 times 10 to the negative 8. So 1868 would be the correct answer for that one. Okay. For this one, when carbon dioxide dissolves in blood, it forms a weak acid called carbonic acid, which influences pH blood. The rapid shallow breathing that occurs during the hyperventilation is a decrease in carbon dioxide levels. So based on the information, hyperventilation would cause the concentration of carbonic acid. So CO2 plus H2O makes this carbonic acid. You can find carbonic acid in your data booklet. So the more CO2, or what is this? Rapid shallow breathing that occurs during hypoventilation will decrease. So if we have less CO2, we're going to have less carbonic acid. So if we have less acid, so it's going to decrease, so we can get rid of these guys. And the pH of our blood, if we have less acid, it's going to increase. And this we have, propane, our good friend. So propane is a compressed gas and it is flammable. So D is going to be our correct answer. And this is another typo on this label. You can see that we need gloves for it. We need goggles, and it's flammable. The health hazard isn't very big. The fire hazard is pretty big, but it's not very reactive. So anything that says reactive, we want to get rid of. So D, it says dangerously reactive. C says dangerously reactive because it's not really reactive. And then, so highly flammable or highly corrosive may cause skin irritation. So it looks like it's more flammable because of the 3 here than an actual health hazard. So B would be the best answer for this one. Okay, so we're going to be learning about acid deposition today. So it's got a lot of curriculum points, outline chemical reactions that produce air pollutants. So sulfur dioxide, nitrous oxide, these are the two that we're going to focus on when combined with water. Describe the biotic and abiotic components, so there's some key terms that you need to know. And identify and explain how human activities and natural events contribute to acid deposition in the environment. Plot on a map the acid deposition is influenced by prevailing winds. So this is kind of a weird one. We'll talk about that. Explain how buffers, we need to know about buffers, maintain a relatively constant pH when a small amount of acid or base is added. Explain the importance of maintaining relatively constant pH in a living system. Explain what is meant by buffering capacity, so this is another term we need to know. And evaluate methods used to reduce the incidence of acid deposition and photochemical smog. So two key terms that you need to know. And we need to know about biomagnification. I'm not sure why that one came up last, but yeah. So combustion. So combustion reactions involve reactions with a fuel and oxygen. So combustions always create emissions, and the type of emissions that you get depend on the type of the fuel. So we're going to be looking at hydrocarbon combustion, which you did in grade 10 science. We're going to be looking at oxides of sulfur, and we're going to be looking at oxides of nitrogen. So hydrocarbon combustion is a very common one. Hydrocarbon combustion always has a carbon and a hydrogen, and these N's just represent different numbers. For example, propane could be C3H8. That's the formula for propane. So the N would be 3 and the N would be 8. So that's what that means. They always need to combine with oxygen, and they will always make CO2 and H2O gases. And they create gases because combustions are hot, so it turns those into gases. So the reactants are always a hydrocarbon, carbon and hydrogen. Sometimes oxygen is in there as well. And then oxygen as well. So sometimes oxygen can be with these hydrocarbons as well, which we'll see with some examples. So the products are always carbon dioxide and water with the hydrocarbon combustion. So what makes combustion bad is combustion creates CO2, and CO2 is a greenhouse gas. And lots of us know about greenhouse gases, and we know that they're bad, but we don't really know why they're bad. So they can lead through global warming through the greenhouse effect. So I'll just use this little demo here to explain what happens with the greenhouse effect. So these clouds represent, they're not regular clouds, so there's CO2 in the air. And when light travels from the sun, it travels in different waveforms, which we'll learn about in our physics unit. So one type of waveform is ultraviolet light. So these ultraviolet waves come to Earth, and they're able to pass through the clouds, no problem. And then they hit a rock, and they will warm up that rock, and then they'll hit a tree, they'll warm up that tree. And when they warm up that tree, they don't change, they don't stay in that ultraviolet form. What they do is they turn into these longer wavelengths called infrared. And these infrared waves aren't able to travel through the CO2 clouds, so they'll bounce back and go back to Earth. So because energy is coming in this form of this ultraviolet waves, but it's not allowed to leave as this infrared type of radiation, it warms up the Earth more and more. So the more CO2 we have, the more it warms the Earth, which is a good thing and a bad thing, because we want a little bit of warming because our Earth would be a lot colder. We just don't want to increase it by too big of an amount. So these are some examples of balancing. So I'll just walk you through them. So you did balancing in grade 10, but we'll do it again. So hydrocarbon combustion always makes CO2 and H2O gases, so you can fill in those. So when balancing these, you want to balance the carbons first and then the hydrogens. So we have 2 carbons over here, so we want 2 carbons over here, and we have 6 hydrogens over here, so we want to put a 3 in front because 3 times 2 is 6. Now we're going to leave our oxygens to the last, and we want to count up our number of oxygens. So 2 times 2 is 4, so these have 4, and 3 times 1 is 3. So we have a total of 7. So we can use that to balance these oxygens. So 3.5, it's fine to use. 3.5 is fine. 3.5 times 2 gives us 7, so there's 7 oxygens on both sides. So let's try another one. So again, we're going to make CO2 and H2O. So we have 4 carbons here. So we're going to have 4 carbons here. We have 10 hydrogens here. And there's always a 2 by the H2O, so 5 times 2 is 10. Now let's count up our oxygens. So 4 times 2 is 8, and 5 times 1 is 5. So if we add up those, that equals 13. And to get 13, it's going to be 6.5. 6.5 times 2 will give us 13, so there's 13 on both sides. And this last example here is one that you'll see. So methane is CH4, and lots of people get confused with this, but remember, you always need oxygen to burn things, and you'll always get CO2 and H2O. Okay, so we balance our carbons first. There's 1 carbon here, 1 carbon here. We're all good. We have 4 hydrogens here, so 2 times 2 is 4. And now we'll count up our oxygens. We have 2 from our CO2, and then 2 times 1, we have 2. So that gives us a total of 4. 2 times 2 is 4. Okay. So that's just a quick balancing. It's not a big thing in Science 30, but sometimes you will have to, look at balancing. So I just want you to be aware of that. So sulfur is another pollutant that's found in things, and these are the 2 most common ways that you can find it in sulfur. So it's found in coal. So coal is just pure carbon. So that's carbon solid, not carbon 5. So when we burn carbon, it makes CO2, right? And CO2 is a greenhouse gas, so that's not great. But this sulfur is a lot worse. So sometimes in coal, you have contaminants like sulfur. And sulfur is found as S8. The 8 doesn't really matter, but sometimes you have that contaminant of sulfur. And when that sulfur combines with the oxygen, it makes SO2. And this SO2 is bad. This is what leads to acid rain, and that's not what you want. Another way that you can find it is hydrogen sulfide and sour gas. So if you burn sour gas, you'll make, we're burning it, so we need our oxygen. So hydrogen and oxygen will make H2O, and then the sulfur and the oxygen will make that SO2. And remember, this SO2 is bad, so we don't want that SO2. So acid deposition is when sulfur, nitrogen, or carbon dioxide combine with water in the air, moisture in the air, they make acids. So the worst one, I'll start with the worst one, is this SO2. So when we get that SO2 from burning coal, that's the number 1 way that we get it. It combines with water in the air. And when it combines with water in the air, it makes H2SO3. So this process, this chemical reaction here, is called acid deposition. And this is bad. This is sulfurous acid. Sulfurous acid. And that's the main cause of acid rain. So nitrogen can also do that as well. So if you have something like NO2 in the air, it combines with H2O, and it can make nitric acid, HNO3, and then carbon dioxide can do this too. These two are to a lesser extent, but it can make carbonic acid, like that sample diploma question was talking about, and this is another type of acid. But this is the main one that you need to know. Sulfur from burning coal makes this sulfurous acid, and that's what makes acid rain. So acid deposition is when emissions combine with water to form acid rain. emissions that are from human sources are called anthropogenic. So not all acid rain is caused by human sources. Volcanoes cause a lot of acid rain, and that's not human caused. So the definition of acid rain is anything that falls with a pH of less than 5.6. So if your rain has a pH of 6, it wouldn't be considered acid rain. So negative effects of acid rain include corrosion. I think it's not next to S in there. Corrosion of cars, statues, roads. There are some misconceptions about acid rain that they'll like burn your eyes or something like that, but it won't. That's not the main cause of acid rain. It mostly just corrodes things. So you need to know about wind patterns in Canada. So here's Canada right here. And what we get is the wind called the westerlies. So the reason they're called the westerlies is because they come from the west. So wind in Canada always blows, not always, but most of the time blows from west to east. So most of our wind will blow into Saskatchewan. Okay, abiotic and biotic factors. So abiotic factors are non-living parts of an ecosystem. So soil, rocks, bodies of water, those are all non-living parts. And biotic factors are living parts. So those are the plants, animals, insects. And acid deposition affects both of these factors, and it decreases biodiversity. So it decreases the type of life that can live. So if you have a lake that is acidified from acid rain, then it's not going to have
Our planet's diverse, thriving ecosystems may seem like permanent fixtures, but they're actually vulnerable to collapse. Jungles can become deserts, and reefs can become lifeless rocks, even without cataclysmic events like volcanoes and asteroids. What makes one ecosystem strong and another weak in the face of change? The answer, to a large extent, is biodiversity. Biodiversity is built out of three intertwined features: ecosystem diversity, species diversity, and genetic diversity. The more intertwining there is between these features, the denser and more resilient the weave becomes. Take the Amazon rainforest, one of the most biodiverse regions on Earth due to its complex ecosystems, huge mix of species, and the genetic variety within those species. Here are tangled liana vines, which crawl up from the forest floor to the canopy, intertwining with treetops and growing thick wooded stems that support these towering trees. Helped along by the vines, trees provide the seeds, fruits, and leaves to herbivores such as the tapir and the agouti, which disperse their seeds throughout the forest so they can grow. Leftovers are consumed by the millions of insects that decompose and recycle nutrients to create rich soil. The rainforest is a huge system filled with many smaller systems like this, each packed with interconnected species. Every link provides stability to the next, strengthening biodiversity's weave. That weave is further reinforced by the genetic diversity within individual species, which allows them to cope with changes. Species that lack genetic diversity due to isolation or low population numbers are much more vulnerable to fluctuations caused by climate change, disease, or habitat fragmentation. Whenever a species disappears because of its weakened gene pool, a knot is untied and parts of the net disintegrate. So, what if we were to remove one species from the rainforest? Would the system fall apart? Probably not. The volume of species, their genetic diversity, and the complexity of the ecosystems form such rich biodiversity in this forest that one species gap in the weave won't cause it to unravel. The forest can stay resilient and recover from change. But that's not true in every case. In some environments, taking away just one important component can undermine the entire system. Take coral reefs, for instance. Many organisms in a reef are dependent on the coral. It provides key microhabitats, shelter, and breeding grounds for thousands of species of fish, crustaceans, and mollusks. Corals also form interdependent relationships with fungi and bacteria. The coral itself is a loom that allows the tangled net of biodiversity to be woven. That makes coral a keystone organism, one that many others depend on for their survival. So what happens when destructive fishing practices, pollution, and ocean acidification weaken coral or even kill it altogether? Exactly what you might think. The loss of this keystone species leaves its dependents at a loss too, threatening the entire fabric of the reef. Ecosystem, species, and genetic diversity together form the complex tangled weave of biodiversity that is vital for the survival of organisms on Earth. We humans are woven into this biodiversity too. When just a few strands are lost, our own well-being is threatened. Cut too many links, and we risk unraveling it all. What the future brings is unpredictable, but biodiversity can give us an insurance policy, Earth's own safety net, to safeguard our survival.
So another bad thing with acid rain is that it affects soil pH. So these are different plants, and these are their optimal soil pH. So if you have acid rain, which is anything below 5.6, so less than 5.6, what you'll find is that alfalfa will not grow, barley will not grow, blueberries will do just fine, canola doesn't grow very well, this won't grow, this won't grow, this won't grow, this won't grow very well. This won't grow, potatoes would do okay, and this wouldn't grow very well, but the types of plants that you can grow diminish quite a bit. So this is what I'm talking about with biodiversity. So some things can live in acidic conditions, but not as many things. So if you had a pH of, I don't know, 6.5, you could see that you could grow a lot more stuff if that was your pH of your soil, if it was around 6.5. So acid deposition can lead to a problem in plants' ability to absorb nutrients. So there might be nutrients in the soil, but they're unable to absorb those nutrients in their roots. So the thicker the line here, the better it can absorb. So you can see everything has a really thick line right around 7, so a neutral pH. But as we get more and more acidic, the line gets thinner. So that might mean that there's lots of phosphorus in the soil that plants need. They just won't be able to absorb it. Right? There's lots of molybdenum in the soil, but those plants won't be able to absorb it. So same thing with basic soil, they can't absorb that iron that they need. So it's important to have a neutral pH, and your plants will be able to get all of your soil. So another problem with acid rain is leaching. So leaching is when you take a solid and turn it into a liquid, and it can enter the soil and water systems. So normally aluminum is found like this in soil, and as long as it's a solid, it's not that bad. It's not very soluble, so if you put a lot of water in it, that aluminum won't go into the soil. But when acid is acid to the soil, it breaks down this and it turns them all into aluminum ions, and those aluminum ions are soluble. They go into the water, and then you drink that aluminum, and it's not good to drink metals, or it's not good to have metals in your plants. So this can lead to decreased plant growth, prevent absorption of calcium, and reduce decomposing soil and bacteria. So it can wreck your soil if you're a farmer. So mercury is a really bad one. Mercury is found in solid form in very small amounts in soil. So again, if it's in solid form, it's not as dangerous to us. But when it mixes with acid, it creates these ions, and these ions can enter our water, and mercury can't be removed from living systems. So what happens is it continues to build up and build up and build up. So as you get older and older, your mercury levels get higher and higher, and at a certain point it can become toxic and kill you. So this leads to biomagnification. So this is a key term. This was in our curriculum points that we needed to know. So the biomagnification is higher and higher out. Pollutant levels higher and higher in the food chain. So I have a picture on the next slide that shows that idea. So this is bioaccumulation. You don't need to know that. It just, if you live in a contaminated body of water for a long time, as you get older and older, your levels are going to get higher. You don't need to know that. What you do need to know is biomagnification. This is important. So this is where you have small amounts of pollutants in things lower in the food chain, but this one fish may eat 100 of these shrimp. So if it eats 100 of the shrimp, you can see the fish has a higher level. Well, the seal may eat 100 of these fish. So it eats 100 of these fish, so the seal has a higher level of mercury in it, and then this polar bear may eat 5 of these seals, so the polar bear is going to have an even higher level. So with biomagnification, we see higher and higher contamination levels higher in the food chain. So the highest in the food chain is going to be your highest levels. So how do we reduce our impact of acid rain? So acid rain is bad. How can we prevent it? Well, limestone is a material that can do this for us, and limestone is a naturally occurring material. So what limestone has, and this calcium isn't really important, but limestone is calcium carbonate. It's this carbonate that is important. So carbonate can act as a base. So it's got a, if we get rid of the calcium, it has a 2- charge. And if I pour a bunch of acid in a lake with limestone, what happens is this carbonate acts as a base, and it'll take that extra hydrogen from my hydronium. So this is my proton donor. So that's my acid. And this is my base. And what it ends up turning into, well, H3O plus turns into H2O. Now it's not an acid anymore. And then CO3 minus gained a hydrogen, so it turns into this. So it removes this hydronium, so it removes the acidic material from the lake. So buffering, so this is a buffer. So limestone is a natural buffer. So buffering is a resistance to change in pH. So they're usually made of weak acid conjugate base pairs. So we talked about conjugate acid base pairs before the break, but what a conjugate acid base pair is if this is an acid, then its conjugate base is going to be the same thing without having that H on there, right? So the buffer one is an example of this. So in the buffer, we had the acid. This is what we made. And we also had CO3 2- here. So these are acid-base pairs, and they're weak, right? They're not one of those top 3 from our data book. So that's what makes a weak acid-base conjugate pair, and any of these can act as buffers. So this is the most common one that you'll see. So it's done by removing hydronium, like we saw in the last example, and once the buffer is used up, it reaches buffering capacity. So there's only a certain amount of limestone that we can have in there. So once we use up all this carbonate, we've reached our buffering capacity, and all of a sudden we'll see our lake pH skyrocket. So this picture is kind of funny because this was an idea to reduce acid deposition. So this is a coal plant. So in here, they're burning coal with oxygen to make CO2. And that CO2 escapes out this smokestack. So remember, coal also has sulfur in it, and that sulfur makes SO2, and that's bad. That's the leading cause of acid rain. So they're like, hey, maybe if we make our smokestacks bigger, maybe that SO2 will go in the upper atmosphere and it won't go in the lower atmosphere, and it won't cause acid rain. Well, they were super wrong. That didn't work, and they built these huge smokestacks, but it didn't help anything at all. You can see this is a regular smokestack here, and this is bigger, and it was just a way of trying it, and it didn't work out. So this is an actual way that works. So these are called scrubbers. So when you have coal, it gives you carbon and sulfur, and you burn it. So when you burn it, you make CO2 and SO2. So what they add to it is they add this calcium carbonate, really similar to the limestone, right? Same idea, but this time they burn it and it creates this calcium oxide. And what happens is calcium oxide and sulfur dioxide mix in here, and instead of it turning into a gas, it turns into this solid, it turns into a wet slurry that they can collect, and it doesn't get released in the atmosphere. So out of the smokestack here, all you get is CO2, which is not great, but it's way better than CO2 and SO2. So this is one way of preventing acid rain. So these are another pollutant that you need to know about, NOx. So nitrogen is found in our atmosphere. Nitrogen is N2, and about 79% of what we breathe in, our air, is nitrogen. So there's a lot of nitrogen around. So nitrogen is normally not reactive, but if you put nitrogen next to something that's really hot, then it's going to react with oxygen in the air. So nitrogen reacts with oxygen. It can make NO2, and nitrogen can react with oxygen, and it can make NO. And that's why we call it NOx, because it can be NO2 or NO1. So it just sort of encompasses both of these ideas. So most common cause of these reactions are high temperature combustion processes. So this is cars and furnaces. So anything that's really hot will cause the nitrogen and the oxygen to mix together into these guys, which are not good. So cars are the most common source of NOx's. So what NOx leads to is photochemical smog. And I don't know if you've read the stories about China and how pollution levels have gone down. Well, China's got a problem with photochemical smog. So when they were all in lockdown, no one was driving any cars, so they didn't have this haze over their city. But of course, it's back up again since they're out of quarantine. But photochemical smog is a brownish haze that appears over cities, and photochemical smog is most commonly caused by NO2. It can irritate eyes, nose, throat, and it can be bad for people with lung issues like asthma. So it's just an irritant in terms of if this had a Wemyss symbol on it, it would sort of have that guy with the exploding chest, because it's not going to kill you, but it's just something that you don't want to be around all the time. So ground level ozone ozone in the atmosphere is good. It helps protect us from damaging UV radiation, which can cause skin cancer. But if you have ozone near the ground, it's bad, and it contributes to something called volatile organic compounds. So what ozone is ozone is O3, and it mixes with these NOx's, and it can increase photochemical smog, and it can cause irritants. So ground level ozone is bad because it can cause respiratory problems, and it also needs these NOx's. It leads to those NOx's as well. So here's a video on catalytic converters. This is a way of reducing NOx's, and all cars have these. So that's the video. I'll post an assignment as well after you watch the video, and you can do it, and I'll go through the assignment tomorrow. You don't have to hand these assignments in or anything. They're just for you. We'll have a quiz at the end of this and see if you guys actually watch my videos. Okay, so thanks for listening, and yeah, enjoy this lesson.
We take it apart so you don't have to. A multitude of cars. In each one, a motor burns fuel and produces toxic gases, nitrogen oxides, carbon monoxide, and unburnt fuel residue. Luckily, each car also has a catalytic converter. Located under the hood, attached to the motor, right before the exhaust system. Gases produced by the motor go straight into the catalytic converter and come out the other side less than 1/10 of a second later. The converter gets less than 1/10 of a second to recombine toxic gas molecules and produce harmless substances like water vapor and oxygen. How? To understand it, we've got to destroy it. The stainless steel housing contains 2 ceramic blocks. Each block is filled with thousands of microducts. Their sides are coated with precious metals. Precious? Platinum and rhodium in the first block. Platinum and palladium in the second block. Metals that can cost more than $100,000 a pound. But they're worth every penny. Together, they have the extraordinary property of causing toxic gases to react and then recombine, producing gases that are harmless to your health. All that without altering themselves or rusting. Precious. The trick is to maximize the contact zone between gas and metals. That's why there are so many microducts, almost 400 per square inch. Their combined surface area matches that of a football field. A laboratory as big as a football field, but folded onto itself in order to remain small. The transformation of gas from toxic to non-toxic happens most efficiently when the catalytic converter is hot. Very hot. 1,300 degrees Fahrenheit. It's the toxic gases themselves that heat up the catalytic converter. They exit the motor at temperatures as high as 900 degrees Fahrenheit. The chemical reactions inside the catalytic converter also generate heat, transforming the converter into a super efficient furnace designed to break down and reform gas molecules. Let's take a closer look at these mysterious transformations. The nitrogen oxide and carbon monoxide molecules, along with the molecules of unburnt fuel residue, enter the catalytic converter. They're swallowed up by the thousands of microducts. As they reach the platinum and rhodium in the first block, nitrogen oxide molecules are the first to react. These metals break down the molecules by withholding one of their atoms. The freed atoms stick to each other and recombine. The result? Nitrogen oxide molecules become oxygen and nitrogen, which already make up 99% of the air that we breathe. The gas molecules now head into the second block, where the microducts are coated in platinum and palladium. These precious metals withhold oxygen. The intense heat here forces the carbon monoxide molecules to combine with the oxygen. The result? Carbon dioxide, the same gas that creates bubbles in soft drinks. Now for the molecules of unburnt fuel residue. At these extreme temperatures, their encounter with the oxygen forces them to recombine. The result? More carbon dioxide and water. All that in less than 1/10 of a second. In theory, the catalytic converter can eliminate 99% of a motor's toxic gases. In reality, it's inefficient as long as it's not hot. A car has to travel about 6 miles before the catalytic converter reaches its ideal operating temperature. That's 6 miles spewing untreated gases. In spite of the catalytic converter's best efforts, the car remains a source of pollution. But thanks to this miniature laboratory, it emits 5 times less pollution. That's still pretty impressive.